Now that we know what the model selection problem is, let's think about how we're going to solve it. So in this video, we'll talk about some Bayesian approaches. So coming from a Bayesian perspective, how you might approach the model selection problem. So the setup here is going to be that we're going to have, let's think about regression or classification. So we have some probability distribution on y given x, and before we would have just had theta here, some parameters theta describing our model, but now we're going to have a class of models, and the class of models will be indexed by m. I'll put this little m to denote which model in the class we're considering. So we'll have, for any given m, this will define a model. And m would be, for example, in the examples that we talked about, m might be the number of basis functions in a linear regression function, a linear regression model, or it might be the variance for a hyperparameter, or some other a hyperparameter being a parameter of the prior distribution, or it might be some other complexity controlling parameters. So we separate those out from theta. And theta, as usual, if we're being Bayesian, we put some prior on theta. So theta is a random variable, and let's call it capital M. So capital M is going to be a random variable that takes these values little m, and that will be our model random variable. So this is a class of models. And if we're being Bayesian, we set up we just assume our distributions, our priors, and we just use the rules of probability. That's what being Bayesian is. And so what we're interested in is this predictive distribution on y's given x's and given x and our data. And how are we going to compute this? Well, we need to integrate out our model. We also, it's already integrated out, but let's write out explicitly what that looks like when we integrate out the model. So we have the integral of the probability of y given x, the data, and the model, times the probability of the model given x and the data, integrating with respect to the model, little m. And this could be, okay, before I get to that, then this factor here, usually we assume x is some fixed non-random thing in this type of setup. So this is just, it's the usual thing. X is just the value that we want to predict y for. So this is just the probability of the model given the data, integrating with respect to m. And m, here I wrote it as an integral, but if m were a countable, if it were a discrete random variable, or took values in a finite set, this would be a sum, or it could be some combination of the two, a sum and an integral. But it's whatever is appropriate. In a general, we'll just use an integral, and you can generalize it to a sum or whatever makes sense for the particular situation. So now, this looks a lot like before when we just integrated. We had this similar sort of thing with theta instead of m. So what's the difference? Well, the difference is this part has already marginalized out theta, right? Let's write that out. What does that look like? This factor here equals the integral over theta of the probability of x given the data. Actually, we can just go ahead and drop d and the model, because that theta is going to be y is going to be independent of the data given theta, times the probability of theta given all this stuff, x, data, and model. And then again, by the same reasoning, we can just drop x here. So here we've already integrated out theta, and this is the posterior distribution on theta given the data for that particular model. So since and remember, theta is not a complexity controlling parameter, because all the complexity controlling parameters are over here in m. Theta is the parameters that are being used to fit the data. So by integrating over theta, this is not going to, this type of thing, it's not sort of over, it's already averaging over theta, so it's not sort of overfitting. So you can think about this as averaging over the probabilities that are being predicted under each of these different models, where the weights that we're averaging with are the posterior distributions on the model, the posterior distribution on the model given the data. So this is a posterior distribution on the model given the data. And this is called, so if we were to use this is called Bayesian model averaging. Bayesian model averaging, or BMA. And this is just, there's nothing really sort of fancy about this. This is just being Bayesian, just being fully Bayesian. Nothing sort of especially clever. Now, sometimes this might be a really hard integral to compute. And so an often used alternative is to approximate this sum by putting a point mass at the value for which this posterior is maximized. So we would approximate this by the probability of y given x, the data, and m star, where m star is a maximizer of the probability of the model given the data, over maximizing over models little m, model parameters little m. So m star it's sort of a map estimate. It's a maximum a posterior estimate for the model, right? So to be precise here, I should put, because there might not be a unique maximizer, a value theta, a value m star that maximizes this. So thinking about this as a set. And this is called, well, I don't know if there's if this is a standard name, but a good name for this is type 2 maximum a posteriori. And the reason why I think that's a pretty good name is because type 1, or not type 1, type 2 maximum likelihood is when you do the same thing, so all of this just the same. And for m star, you take the argmax, the maximizer of the probability of the data given the model. And this is called type 2 maximum likelihood. You could think about this here as a sort of likelihood function, right? The probability of the data given the model, that's a lot like when we had the likelihood function. A likelihood function was the probability of the data given theta, the probability of the data given our parameters. And this here, this is called, by analogy with the likelihood function, the probability of the data given the model is called the marginal likelihood. The marginal likelihood. And so this is sort of, it's sort of maximum likelihood, but it's type 2 because you're sort of a level above the parameters. So this thing I was talking about before, how since this thing here is already averaged over the parameters theta, choosing this m star in either of these cases really, it's not really overfitting, because I shouldn't have talked about overfitting in this one. So for the overfitting, that sort of comment applies here when you're choosing this point estimate for the model, but you're not overfitting really because you're already averaging over all the possible data fitting parameters theta. Theta, it has all the parameters which are being used to fit the particular data that you have. And you're averaging over those already, so this is not overfitting. And I think you can probably see that, as usual, maximum likelihood is a special case of maximum a posteriori if you take a uniform prior on models. Or it might have to be an improper prior if you can't normalize, if you can't put a proper prior over the model. A uniform, if a uniform prior over the models is not a proper prior, then it would be an improper prior. But since the posterior is proportional to the posterior on models is proportional to the marginal likelihood times the prior on models, then if this was uniform, right, then it would just be proportional, and so maximizing one is the same as maximizing the other. And this has a couple other names here. This type 2 maximum likelihood is also called the evidence approximation. Sometimes people call it the evidence approximation. And sometimes people call this also empirical Bayes. That's not a very informative name, sort of misleading name actually. But sometimes people call this empirical Bayes. And that's just the same thing as type 2 maximum likelihood, same thing as evidence approximation. And I called this one type 2 map, but this is not really a standard, so let me put like a star here. This is not a standard thing. I don't think I've seen it actually called this anywhere, but in order to explain it, I haven't seen this actually given a name. So in order to just give it a name for you to think about, I think the most natural name would be type 2 map, because there's the obvious sort of correspondence between these two. All right, so those were some Bayesian approaches to model selection. And I guess really, these last two were actually model selection approaches because we were choosing a particular model M star, right? This one, first one, Bayesian model averaging, it's not really model selection because you're not choosing a particular model. But it's sort of, you could think about it as sort of with this interpretation of averaging over models. You're sort of, selecting some more than others. So model selection is not really, I guess, the completely appropriate way to refer to this, but it serves the same purpose as the others. So next we're going to look at these were some Bayesian approaches to model selection, and there's also a lot of non-Bayesian ways to approach model selection, and we'll look at those next time. Okay, see you soon.